Title of the module: The Inverse of a Matrix. In this session, we will define what is meant by the inverse of a matrix. We will learn how to evaluate the inverses of transpose of a matrix, product of matrices, and inverse of a matrix. We will get to know about elementary matrices. Various characterizations of invertible matrices will also be covered. Some key results related to invertible matrices will be discussed. Sufficient examples will be provided to give you a clear idea of the topics covered. The definition of the inverse of a square matrix. The inverse of a square n cross n matrix A is another n cross n matrix denoted by A inverse such that A inverse A is equal to I, which is equal to A inverse, where I is the n cross n identity matrix. That is, multiplying a matrix by its inverse produces an identity matrix. In fact, A inverse is uniquely determined by A. A point to note: all square matrices have an inverse matrix. If the determinant of the matrix is 0, then it will not have an inverse. A matrix that is not invertible is called a singular matrix, and an invertible matrix is called a non-singular matrix. We shall see some theorems. The first theorem: let A be the square matrix A, B, C, D. If AD minus BC is not equal to 0, then A is invertible and A inverse is equal to 1 by AD minus BC into the matrix D minus B minus C A. If AD minus BC is equal to 0, then A is not invertible. The quantity AD minus BC is called the determinant of A, and we write determinant A is equal to AD minus BC. So, the theorem says that a 2 cross 2 matrix A is invertible if and only if determinant A is not equal to 0. Theorem 2: if A is an invertible n cross n matrix, then for each B in R power n, the equation Ax is equal to B has the unique solution x is equal to A inverse B. The proof: take any B in R power n. Clearly, we can say that the equation Ax is equal to B has a solution because if A inverse B is substituted for x, then Ax is equal to A times A inverse B, which is equal to A inverse times B, which is equal to I into B, which is equal to B. So, A inverse B is a solution. To prove that the solution is unique, show that if U is any solution, then U must be A inverse B. Now, clearly, since AU is equal to B, we can multiply both sides by A inverse and we obtain A inverse AU is equal to A inverse B, which is equal to 1U, which is equal to IU, which is equal to A inverse B, and U is equal to A inverse B, which implies the solution is unique. The next theorem, theorem 3: if A is an invertible matrix, then A inverse is invertible and A inverse the whole inverse is equal to A. If A and B are n cross n invertible matrices, then so is AB, and the inverse of AB is the product of the inverses of A and B in the reverse order. That is, AB the whole inverse is equal to B inverse A inverse. If A is an invertible matrix, then so is A transpose, and the inverse of A transpose is the transpose of A inverse. That is, A transpose the whole inverse is equal to A inverse the whole transpose. Proof of A: since A, the matrix A, is invertible, A inverse is equal to A inverse A, which is equal to I. So, by the definition of invertible matrix, A inverse is invertible. That is, A inverse A is equal to A inverse is equal to I, the identity matrix. Therefore, the inverse of A inverse is A, that is, A inverse the whole inverse is equal to A. B, since A and B are invertible, A inverse is equal to A inverse A, which is equal to I. B inverse is also equal to B inverse B, which is equal to I. Also, determinant A is non-zero and determinant B is also non-zero. Therefore, determinant AB is equal to determinant A times determinant B, which is non-zero. Hence, this implies that AB is also invertible. Next, we need to prove that AB the whole inverse is equal to B inverse times A inverse. Now, AB into B inverse A inverse is equal to A times B inverse times A inverse. This is by the associative property. So, instead of B inverse, we can substitute I. Therefore, A inverse is equal to A inverse, which is equal to I once again. Similarly, B inverse A inverse times AB is equal to B inverse times A inverse A times B, again by associative property, which is equal to B inverse times IB, which is equal to B inverse times B, which is equal to I. That is, AB times B inverse A inverse is equal to B inverse A inverse times AB, which is equal to I. Therefore, AB the whole inverse is equal to B inverse times A inverse. C. First, we want to prove that the determinant of A transpose is not equal to 0. We know that the determinant A transpose is equal to determinant A, and so A transpose is invertible. Next, we need to prove that A transpose the whole inverse is equal to A inverse the whole transpose, and so A transpose times A inverse the whole transpose is equal to A inverse times A the whole transpose, which is equal to I transpose, which is equal to I. Similarly, A inverse transpose times A transpose is equal to A inverse the whole transpose, which is I transpose, which is I. Therefore, A transpose the whole inverse is equal to A inverse the whole transpose. A point of remark: the product of n cross n invertible matrices is invertible, and inverse is the product of their inverses in the reverse order. Elementary matrices. An elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. The next example illustrates the three kinds of elementary matrices. Something to note here, row n means the nth row and the column m means the mth column. Definition: if an elementary row operation is performed on an m cross n matrix A, the resulting matrix can be written as EA, where the m cross m matrix E is created by performing the same row operation on IM. A point of note: each elementary matrix E is invertible. The inverse of E is the elementary matrix of the same type that transforms E back into I. Fourth theorem: an n cross n matrix A is invertible if and only if A is row equivalent to In, and in this case any sequence of elementary row operations that reduces A to In also transforms In into A inverse. Proof: suppose that A is invertible, then since the equation Ax is equal to B has a solution for each, A will have a pivot position in every row. Now, since A is square, the n pivot positions must be on the diagonal, which implies that the reduced echelon form of A is In, that is A tilde In. Conversely, suppose that A tilde In, then since each step of the row reduction of A corresponds to the left multiplication by an elementary matrix, there exists elementary matrices E1, E2, so on up to EP, such that A tilde E1A tilde E2 in times E1A tilde so on up to tilde EP times EP minus 1 so on up to E1A, that is equal to In. That is EP times EP minus 1 so on up to E1A is equal to In. Since the product EP so on up to E1 of invertible matrices is invertible, we get EP times so on up to E1 the whole inverse EP so on up to E1 times A, which is equal to EP minus 1 so on up to E1 the whole inverse times In, and A is equal to EP times EP minus 1 so on up to E1 the whole inverse, that is EP times so on up to E1 times A is equal to In. Thus, A is invertible as it is the inverse of an invertible matrix. Also, A inverse is equal to EP so on up to E1 inverse the whole inverse, which is equal to EP minus 1 so on up to E1. Then A inverse is equal to EP minus 1 so on up to E1 In, which says that A inverse results from applying EP minus 1 so on up to E1 successively to In. This is the same sequence that reduced A to In. Theorem 5, the invertible matrix theorem. Let A be a square n cross n matrix, then the following statements are equivalent. That is, for a given A, the statements are all true or all false. A, the matrix A is an invertible matrix. B, A is now equivalent to the n cross n identity matrix. C, A has n pivot positions. D, the equation Ax is equal to 0 has only the trivial solution. E, the columns of A form a linearly independent set, and F, the linear transformation x to Ax is 1 to 1. The equation Ax is equal to B has at least one solution for each B in R power n. The columns of A span R power n. The linear transformation x to Ax maps R power n onto R power n. There is an n cross n matrix C such that Ca is equal to 1. There is an n cross n matrix D such that Ad is equal to 1. A transpose is an invertible matrix. Theorem 6, let T from R power n to R power n be a linear transformation and let A be the standard matrix for T. Then T is invertible if and only if A is an invertible matrix. In that case, the linear transformation S given by S of x is equal to A inverse x is the unique function satisfying 1 and 2. We shall see some examples to understand matrices better, especially the inverse of a matrix. We are now going to see if A and B are inverses of each other. So, to check whether B is A inverse or not, the easiest way to do this is just do the product of both the matrices, and if you arrive at an identity matrix, then you are right. Otherwise, your assumption is wrong. So, we are going to lead with that assumption, and I am going to take AB. So, A is 2, 5, minus 3, minus 7. I just have put it just like that, and I am wondering if B is the inverse of A, and therefore I am just multiplying both, and I am finding that you can do the multiplication on your own. The learner can try doing the matrix multiplication on your own, and you will be surprised to find that you will get this answer 1 0 0 1, which is the 2 cross 2 identity matrix I. And hence I have proved that for A, when I multiply A by B, I am getting this identity matrix. What about B times A? Let us keep in mind that the matrix multiplication need not be the same, that it means that it is not commutative. So, AB need not be equal to BA. in usual matrix multiplication, which is why we double check whether BA is also equal to the identity. Hence, BA is equal to minus 7 minus 5. I just have substituted B here and I have substituted A and I am multiplying and I am seeing whether it works, and yes, I am getting this answer 1001. The learner is once again encouraged to do the matrix multiplication and find the answer and check the answer if it is right. So, I find that AB is also I and BA is also I, which means that A inverse is equal to B. So, the inverse of A happens to be this matrix. So, we move on to one more example. So, A is given to be this 2 cross 2 matrix. I am asked to find A inverse. How do I go about it? First of all, I must check whether my matrix is invertible or not, and for that I check for the determinant. And what is the determinant? It is merely multiplying like this. So, it is 3 times 6 minus 5 times 4. So, if A, B, C, D are given, it is a 2 cross 2 matrix, it is AD minus BC, which is what I have done here. So, 6 cross 3 minus 4 times 5, which is equal to minus 2. Now, this is non-zero. If it were 0, we would say that this matrix does not have an inverse. Since it is non-zero, we say that this matrix is invertible, which means that inverse exists. And to calculate the inverse, this is the formula. So, A inverse is 1 by mod A. So, determinant A times adjoint A. Now, finding the adjoint is pretty easy. So, 1 by minus 2, 6 minus 4. Can you see this column becomes a row, and the row and the column here also becomes a row, except that these opposite terms alone will carry a new negative sign. So, the easiest way is turn this column into a row here and also this column into a row and just invert the positions and also add a negative sign. So, the first time it might seem a little uncanny, but if you continue to practice this technique, you will be able to invert a lot of matrices in this manner. So, finding the adjoint is pretty easy by this technique. So, this is equal to minus 3, 2, 5 by 2 minus 3 by 2. How did we arrive at this? Because we have to divide by 1 by determinant of A. So, there is a division of determinant of A, and determinant of A was minus 2. So, when dividing by minus 2, this is the answer I get, and this happens to be the inverse of this matrix 3, 4, 5 and 6. So, this is one technique to find the inverse of a matrix. There are plenty of other techniques as well. We move on to one more example. Now, this is actually a system of linear equations. For this system of linear equations, I can solve it using you know that there are plenty of methods to solve a system of linear equations. One of these methods is a matrix method. That matrix method is what I am going to show you, and we have discussed this already in the theorem. This problem is merely a demonstration of that theorem. So, imagine if Ax is equal to B, then x is equal to A inverse of B is the solution to this equation, this system of equations. Now, how do I go about a matrix solution is just write. So, if there is 3x1, 4x2, write the row like this 3 and 4, and the second equation it is 5 and 6. So, just substitute 5 and 6 in the second row, and you have two variables, namely x1 and x2. Substitute that here. So, x1 and x2 is equal to 3 and 7. On the right hand side I have 3 and 7, and so I get 3 and 7 here. So, if you multiply 3x1 plus 4x2 is equal to 3 and 5x1 plus 6x2 is equal to 7. So, merely representing the equation in the matrix form. Now, I need to find the inverse. So, I say that x is A inverse B, which means that I need to find A inverse. But to find A inverse, I must first check whether A is invertible or not. How do I find whether it is invertible? I check the determinant, and the determinant A inverse is equal to, for the determinant, determinant A is equal to minus 2. You can check right away if you want. So, 6 into 3 minus 5 into 4, which is 18 minus 20, which comes to minus 2. Again, it is a non-zero term, hence inverse exists. So, since inverse exists, A inverse is equal to minus 1 by 2 and just find the adjoint of this matrix. I am using the same technique. Turn the column into a row, turn the first column into the second row and turn the second column into the first row and just put minus minus here. So, minus 4 minus 5 here, opposite the diagonal terms alone become minus. So, this is suppose if it were minus here, it will become plus. So, keep that in mind. So, then after doing the calculations you get this as your inverse. So, x is actually A inverse B. So, I am multiplying this A inverse into my B. What is my B here? B is 3 7. So, this is my B 3 7. When multiplying I get x to be 5 minus 3. You can check, do the matrix multiplication and check, you will get the answer to be this. So, x1 and x2 are 5 and minus 3 respectively. So, this is a way to solve a system of linear equations using matrices. Now, I am going to use elementary matrices. We mentioned in the earlier material that elementary matrices are those matrices that you arrive at by a single change of the operation to the identity matrix. Now, if you see here E1 1 0 0 0 1 0, this is actually a elementary matrix which has been got from the 3 cross 3 identity matrix. By what operation, you might wonder? You just multiply the row, the first row, that is R1 by minus 4 and you have added it to the last row. So, I am sorry, the last row minus of 4 into R1, that is one way of looking at it. So, the last row minus 4 into R1 will give you this elementary matrix E1. What about E2? So, here it is usually the 3 cross 3 elementary matrix is 1 0 0 0 1 0 0 0 1, right, and but here what do I have? 0 1 0 1 0 0 0 0 1. Surely you can see that this has to be the second row and this was the first row in the identity matrix. Hence, this elementary matrix was got by merely interchanging the position of 2 rows, and the third elementary matrix E3 has been got by multiplying the last row by 5. So, 1 0 0 0 1 0 0 0 1, except the last row I have multiplied by 5. So, single row operation, and here A is another matrix. Now, they are asking you to find E1A, E2A, E3A. I am going to solve this problem in 2 steps, in 2 ways. First way, I am directly going to multiply by E1 by A and second E2 by A and then E3 by A and so on, and I am going to show you how the row operations also play a role there. So, E1A is 1 0 0 0 1 0 minus 4 0 1, as you can see from this here. I have just substituted that here and this is my A. I am multiplying these 2 matrices, right. You can check for yourself that this will be the matrix that you arrive at. Additionally, you can see that this same matrix can be got from E1 by merely doing R3 minus 4 R1, which was how we got E1 in the first place. E1 was a matrix that we got from the identity 3 cross 3 matrix by doing this operation R3 minus 4 R1. Similarly, you can do the same operation on A and still arrive at E1A. So, either you do this ordinary matrix multiplication, you will end up with the same answer, or you can do the same row operation on A and you can get E1A. So, this is a very cool aspect of for elementary matrices. Similarly, for A2, E2A 0 1 0 1 0 0 0 0 1, I am multiplying these 2 matrices, I am arriving at this answer. Clearly, I got this from A by merely interchanging these 2 rows. So, if you interchange these 2 rows, I arrive at this matrix which is my E2A. Once again, E2A was got from the identity matrix by interchanging these 2 rows. So, the same operation when I apply on A, I arrive at E2A, and likewise for E3 you can check. So, this is we can obtain E1A, E2A and E3A by using some row operations. So, this is a very interesting aspect of elementary matrices. Now, we shall find an algorithm to use A inverse. There are plenty of methods to find the inverse of a matrix. We are going to use the row operations, column operation method in order to get the inverse of a matrix. Now, let us say, suppose for example, you are given a matrix A 0 1 2 1 0 3 4 minus 3 8, which is a 3 cross 3 matrix, and in AI, what is AI is merely that I have found an augmented matrix. The augmented matrix is not a big deal. You just have to add the 3 cross 3. Suppose you have a 3 cross 3 matrix, you need to take the 3 cross 3 identity matrix and augment it to my original matrix. So, this was a 3 cross 3 matrix. Now, it has become a 6 cross 3 matrix because I have augmented it to 1 0 0 0 1 0 0 0 1, right, and this will become, and all you need to do is do one row operation after another in order to make sure that this 0 1 0 1 0 0 0 0 1 is now found here on the first 3 columns of this. So, the first 3 columns should be transformed into 1 0 0 0 1 0 and 0 0 1, but instead I am having these terms. To change this into 0 1 0 0, I can do any operations I want. Now, for example, I can merely subtract 1 from this row, these 2 rows can be subtracted and I can get another term here, thereby coming closer to 0 0 1. I can try to make these 2 terms 0 first. So, if I am proceeding in this method, you can again the learner can try and do it on your own. So, when I proceed like this, for lack of space I have done only few operations. You can go all the way to 1 0 0 0 1 0 0 0 1, and in the process what happens is that the entire matrix is transformed, and on the right hand side I arrive at this term, and this is where this set of terms you have, this alone can be extracted to form the A inverse. So, this is the algorithm to find the inverse of a matrix using row column operations. We are now at the end of this session. In this session, we define what is meant by inverse of a matrix. We learnt how to evaluate inverses of transpose of a matrix, product of matrices and inverse of a matrix. We also got to know about elementary matrices. Various characterization of invertible matrices were provided. Some key results related to invertible matrices were also discussed. Sufficient examples were provided to get a clear idea of the topics covered. I hope that this was useful for you. Thank you.